Okay, so up until now, I really spoke only about the case where everything was, so to speak, passive. Passive resistor, passive capacitor, and a battery, passive battery, the battery that is constant. So this was minus 70 millivolt. And this had some value depending on the cell type and size. And this has a capacitance depending on the capacitance of the cell. I didn't tell you much about the values of R and of C, but I want to tell you now, just to give you a ballpark, just to tell you that this R multiplied by C, this time constant that I just mentioned, R multiplied by C, which I call the membrane time constant, is on the order in central neurons in our brain, on the order of 20 milliseconds or so. Milli is 1,000 of 10 to the power of 3. So this is 20 millisecond, much smaller than a second, and that's about the correct time of a typical RC multiplication, RC properties of a patch of membrane in the brain. About 20 milliseconds. It could go down to 10 milliseconds, maybe 5 milliseconds, depending on how leaky is the membrane of this particular cell. But you may remember 20 milliseconds time constant. Okay, so this was the passive situation here. And now I want to go into the synaptic potential. Because I told you before, nobody from the outside inject currents into cells. So where is the source of current to cells? And these are the synapses. So let me draw symbolically a synapse onto this cell. Let's draw it like this. This will symbolize an axon terminating on the cell. So remember that we spoke early on, when we spoke on the anatomy of cells. I hope you remember that typically there were dendrites with spines. So this was a piece of dendrite. And there was an axon going here. And there was this varicosity in the axon. Something like that. So this was the axon. And you remember that there were these vesicles inside the axon full of transmitter. And in the dendrite, in the dendritic spine, there were these receptors. So this was the receptors. And these were the transmitter, the vesicles with the transmitter. And there was interaction between them. So sometimes when there was an action potential, when there was a spike here, and we'll talk about spike later, there was a communication through the synapse. And these receptors absorbed, so to speak, interacted with a transmitter that was now distributed in the space between, in the very small space, not as big as I drew here, but a very small space between the presynaptic axon and the postsynaptic dendritic spine through these receptors and transmitter interaction. So now I'm trying to explain to you what happens in the membrane when you have, in this case, rather than an external source of injection, which was an electrode, a real source of injection or communication, which is the synapse. So this will be my synapse now. So I want to tell you how do we think electrically as a synapse, as an electrical device. You saw that there is a chemical interaction because there is the vesicles that release the transmitter. There are the receptors that picks up this transmitter. What happens then? We know today that something very interesting is happening when the transmitter interacts with the receptor. We know that there are new ion channels open in this membrane. Just because of this interaction between the transmitter and the receptor, there are these new channels which enables new current flow into the cell. So I now schematically mark the interaction between the transmitter and the receptor. This interaction is expressed itself by the opening of ion channels. Channels that enable flow of current, and depending on the type of channels, whether the current will flow from the inside outside or from the outside inside. We'll talk about these channels later on. I just want to explain to you, why do I look now at a synapse as an electrical device? There is, of course, the chemical interaction, but eventually, at the postsynaptic side, at the dendrite side, at the dendritic spine side there, eventually, there is current flow inside or outside through the opening of new ion channels, new path for current. So if I look at the electrical circuit, the passive one, and I want to add these particular new channels that are being opened in the membrane of the cell. So it was the same cell before, but now I added new channels. Let's call it the red channels. This will be our synaptic channels. And these channels in the membrane are open only when there was a transmitter release and interaction with the receptor. I will now draw electrically what I just described by words. I'm saying that in the membrane, in the postsynaptic membrane, there are these channels which behave like a resistor or a conductance. We shall call it G conductance of the synaptic channels, G synapse. These are the new channels that are being opened that enables new current to flow from the outside of the cell to the inside or vice versa. And the direction of current will depend on the value of the synaptic battery, E synapse. Okay, if this battery of the synaptic ion channels, we shall talk about the battery in a second, is more positive inside, the opening of these ion channels will make the membrane more positive inside than the resting potential. Or otherwise, if this is more negative than the resting potential, then the cell will become more negative due to the opening of the synaptic channels. So what I told you is something not easy to grasp. The fact that the transmitter release opens in the membrane of the postsynaptic cell new ion channels, the red ion channels. And these red ion channels enable particular specific ions to flow either from the outside to the inside or from the inside to the outside, depending on which channel is being opened. We'll talk about type of channels in a second. But this is now a full circuit that represents both the passive part that you already studied beforehand and also the synaptic part, the synaptic conductance part. So this is a full postsynaptic membrane consisting of passive properties and synaptic conductance and capacitor.